In this video, we're going to look at using separation of variables to solve differential equations. So let's say we're given some differential equation dy dx is equal to a constant. We'll call that constant c. So what we can do is place kind of a clever trick with the notation. We can move this dx to the other side, and then that's going to give us dy is equal to c times dx. Now to solve this for an equation for y, what we can do is just integrate both sides. So we'll get the integral of dy is equal to the integral of c dx. And that's going to give us y plus our integration constant, and we'll call this one c1, is equal to cx plus c2 for our other integration constant. Now let's put this in terms of y. So we'll get y is equal to cx minus plus c2 minus c1. And if you think about it, subtracting one constant from another constant just gives you a constant. So we'll call this y is equal to cx plus d. Now if you think about it, this solution makes a lot of sense. So our original dE was that if we take a derivative of a function, we get a constant. And we know that if we take a derivative of a linear function like this one, we'll just get a constant, which is the slope. So we can also look at the graph of this. And let's say we have our graph here, and here's our linear function. So the change in y with respect to x at any given point is just the slope, and the slope is constant at all of these points. So let's look at another example. Say this time we're given dy dx is equal to y. So our derivative is equal to our function. Now one way you can think about this is to try and think of a function whose derivative is the same as itself. And we know from calculus that that function would be y is equal to e to the x. But let's say we don't want to think of it like that. Let's say we just want to try and use separation of variables to solve this equation. So we'll go ahead and get rid of this. And now we're going to apply the same process as we did with the last problem. So what we're going to do is move the y to the other side, and we're going to move this dx over here. So doing that, we'll get 1 over y times dy is equal to dx. Now solving this, we'll just integrate both sides again. So the integral of 1 over y dy is equal to the integral of dx. And we remember from calculus that the integral of 1 over y is just going to be the natural log of y plus a constant. And this is going to be equal to x plus another constant. We'll just call it d. Now it's the same thing as last time. If we subtract the c over, we're just going to get another constant. So what we'll have is the natural log of y is equal to x plus, I don't know, I'll just call this e. And then solving for y, we have to exponentiate both sides. So e to the natural log of y is equal to e to the x plus e. And then once we simplify that down, we'll get y is equal to e to the x plus e, or y is equal to e to the e times e to the x, if we remember our algebra rules with exponents. And now again, e to the e is just a constant, because it's just a constant raised to a constant power. So then what we're going to have is y is equal to, I'll call this a, times e to the x. Now this is the same thing we got earlier when we just tried thinking of a solution to this intuitively, which just goes to show that either method can really work, but once we get into a little more complex differential equations, it's kind of hard to think of a solution just intuitively like that. And once the differential equations get more complex, we also can't use separation of variables anymore. But thanks for watching, and go ahead and do me a favor and hit like, and I hope you have a great day.